Scientists just discovered a super ocean deep inside Earth, holding enough water to fill all surface oceans 3 times. That's right. Right beneath your feet, between 410 and 660 kilometers down, is a hidden ocean. Now, it's not the wave-crashing ocean you imagine. The water here is more like a massive, solid water reservoir. We all know Earth's surface is 71% water. Seems like a lot, right? But new research shows the water deep inside Earth might be richer than all surface oceans combined. Can we drink it? Can we dig a tunnel and go for a swim? Hold up. Let's dig in, layer by layer, and find out what this super reservoir is all about. First, we need to understand this. Earth is not a solid ball. It has 3 layers: the crust, the mantle, and the core. Our underground ocean is hiding in the Mantle Transition Zone. This zone is sandwiched between the upper and lower mantle, exactly from 410 to 660 kilometers deep. It's a seriously mysterious area. Scientists were actually studying earthquakes, not looking for water. But guess what? When an earthquake hits, it makes 2 waves, S waves and P waves. They shoot deep into Earth, but their speed changes based on the stuff they travel through. For example, S waves move fast through solids, but they completely vanish in liquid water. The water in the transition zone is locked in minerals as hydroxyl. This drastically slows down the S waves. P waves can pass through water, but their speed is affected too. Analyzing data from dozens of big quakes worldwide, scientists saw some waves suddenly slow way down when they crossed the transition zone. That's weird. The transition zone should just be solid rock. Why is it slowing the waves? They first thought the rock composition was different. Then they ran countless models and lab experiments. In the lab, they recreated the extreme pressure and heat of the transition zone and dropped in common upper mantle rock. The breakthrough: seismic waves only slowed to the observed speed when the rocks contained water. That's when they realized water was hidden in the transition zone. And not just a little, but enough to form a super reservoir. But this underground water isn't sitting in a basin like a surface ocean. It's locked up by a special mineral. You might know this mineral's predecessor, olivine, the most common rock in the upper mantle. Olivine is seriously tough. It's a pale green color, which is how it got its name. Its strongest feature is being heat resistant. It survives just fine even in magma. It makes up nearly half of the upper mantle. We even see it on the surface. Volcanic eruptions drag chunks of mantle olivine up with the magma. When the magma cools and hardens, olivine crystallizes first. If you're lucky, it forms large crystals, which can be cut and polished into jewelry, necklaces, bracelets. They feel great. But as olivine goes deeper, once it hits the transition zone at 410 kilometers, it can't handle it. It loses it. The pressure down there can reach 230,000 times the surface pressure, and temps blast past 1,500 degrees Celsius. In this extreme environment, the crystal structure slams into a complete remodel. From 410 to 520 kilometers, it becomes Ringwoodite. Then, from 520 to 660, it becomes Ringwoodite. These 2 rocks look incredibly beautiful, a blue-green with a glassy shine. Sadly, they are super rare on the surface. Their crystals are tiny, so you can't make jewelry out of them like olivine. They are only found in labs as a precious research specimen. But these 2 blue minerals have a trick olivine doesn't. They can hold water. Their crystal structure has tons of tiny cavities, like little holes in a sponge. They tightly lock water into their structure in the form of hydroxyl groups. Scientists estimate these minerals can hold up to 3% water. That doesn't sound like much, but the transition zone is huge. Do the math, and the total water is more than all surface oceans combined. Insane. These minerals act like a giant water regulator, keeping massive amounts of water stable deep in the mantle. This is key to maintaining Earth's long-term habitability. But here's the next mind-blower. If we have all this water underground, Where did Earth's water actually come from? Scientists have 4 major theories, and each one has its own evidence. Let's break them down. Theory number 1. Earth's native water. Earth formed 4.5 billion years ago. The solar system was a cloud of dust, gas, and small rocks that clumped together via gravity. We used to think the early solar system was too hot. Liquid water would just vaporize. But then we found those original rocks that formed Earth held tons of hydrogen. This wasn't a tiny bit. A single fist-sized meteorite has enough hydrogen to make several liters of water. Earth gathered countless rocks like this. The hydrogen inside slowly bonded with oxygen to form water. This water didn't evaporate. It melted into the mantle, slowly released to the surface by volcanoes, cooled into rain, and filled the oceans. Theory number 2. The asteroid delivery. About 4 billion years ago, the solar system went through the late heavy bombardment. Outer planet orbits shifted, driving a ton of asteroids into the inner solar system. These things slammed into Earth. Scientists analyzed samples from those meteorites and found the water inside was incredibly similar to our oceans. Take the deuterium to hydrogen ratio, a fingerprint for water sources. It matched Earth's oceans almost perfectly. Most comets have twice the ratio. So, asteroids are a much more likely water source than comets. Theory number 3. The Theia impact. This theory is linked to how the Moon formed. Scientists believe 4.5 billion years ago, a Mars-sized planet named Theia crashed into Earth. The collision was brutal. It turned Earth's surface into a magma ocean. Theia was destroyed, and some debris became the Moon. But Theia might have carried water. Instead of boiling off in the magma ocean, this water melted into Earth's mantle. It slowly released later and became part of our oceans. Theory number 4. Earth's self-made water. Early in Earth's formation, the surface was a magma ocean. Hydrogen in the mantle would react with oxygen in the magma, directly creating water. This mainly happened early on, laying the foundation for our water. Today, the HO reaction rate in the mantle is super low. It barely adds new water. These 4 theories aren't mutually exclusive. Earth's early water was likely a combo deal. A little self-made, some from native rock, an asteroid delivery, and a collision top-up. Together, they made the oceans we see today, and the super reservoir hidden underground. Everything we talked about today should blow your mind about water. We have a super ocean larger than the surface one, water locked in mantle minerals, and water sources from multiple channels. There are so many deep Earth secrets behind the water you use every single day. Are you freaked out yet? Doesn't Earth's interior seem weirder than outer space? Scientists still have a lot of unanswered questions about this underground water. Like, how does it flow down there? Could it affect our surface climate? Where do you think Earth's water mostly came from? Asteroids? Or did Earth build it itself? Drop your thoughts in the comments. Let's discuss.